Hi, thank you, David. Good morning, good afternoon, and good evening to some of you. And a warm thank you again to Andrew for sharing updates on ECP with us. So I'm Donny Cooper. I'm with Total's R&D Center based here in Houston and part of a global team responsible for our HPC initiatives. We're now going to shift our focus towards a somewhat new, large-scale, and exciting use case, which in fact dovetails quite nicely with ECP efforts in the area of multiphysics applications and incorporate some of the abstractions and co-design mentioned by Andrew. So we'll introduce a key part of Total's decarbonization effort and how HPC is being used as both an enabler and an accelerator within it, and ultimately how we hope as a business to leverage it to reach net zero, good Lord willing. We have a rock star lineup for you today with three of my colleagues speaking from all around the world. Samuel Lethier, he's the VP of CCUS R&D North America, joining us from Houston. Welcome, Samuel. Herve Gross, he's a senior R&D project manager located in the San Francisco Bay Area. Herve also has a detailed technical talk in the record area on the subject he'll introduce here. And Jorunn Brigtsen, she's a CCUS development manager on the Northern Lights project coming to us from Norway. And we'll also add Sebastian Rossio, CCUS senior development manager based in Paris, to the Q&A. Be sure that we have full coverage of subject matter expertise to best answer your questions at the end. So with no further ado, I'll hand it over to Samuel to get us started on carbon capture, utilization, and storage, an essential technology to a zero carbon future. Samuel?
Okay, so do you hear me? I assume you do. So because we have 45 countries online today, I'm not going to greet you with a good morning, but a simple hello, everyone. And thank you, Donny, for this introduction. So I'm going to start by introducing CCUS and Total's R&D activities with a focus on CO2 capture. Then Herve will highlight a CO2 storage simulation application before Jorunn drives into the Northern Lights full-scale deployment project in Norway. So Herve is located in California, Jorunn in Norway, I'm in Texas. And I just wanted to say that the great thing about remote conferences is that we can participate from all over the globe without having to fly and emit CO2. Okay, let's go. So to maintain global warming below 2 degrees Celsius, CO2 emissions from the energy sector have to fall to zero on a net basis before the end of the century. A portfolio of technologies and approaches is needed to mitigate emissions from increased energy efficiency, fuel switching from coal to gas, deployment of renewable power, and carbon capture, utilization, and storage. CCUS is one of the most cost-effective solutions for CO2-intensive industrial sources, such as the cement and steel industry or the production of hydrogen from natural gas. It's anticipated that CCUS will contribute to 15% of the cumulative reduction in emissions, representing about 5 gigatons of CO2 per year in 2050, which would be equivalent in size to today's oil and gas industry. Mitigation will not be enough to reach net zero globally. CO2 will have to be sucked out of the atmosphere and permanently stored. Negative emission technologies are required to offset the residual emissions, which are either technically too difficult or too costly to avoid. Here also, CCUS has a major role to play through two negative emission technologies, bioenergy CCS or BECCS, and direct air capture. In the first case, biogenic CO2 is captured by the biomass, which is then used to produce power or other products, while the CO2 emitted during the transformation process is captured. Direct air capture is a technology that catches and concentrates the CO2, the atmospheric CO2, ready for transport, use, or storage. So what's CCUS? The CO2 containing waste stream from a power plant or industrial source is diverted from the existing stack to the CO2 capture process. Depending on the source, that stream will contain anywhere from 3 to 50% CO2. The CO2 capture step essentially concentrates the CO2 to higher than 95% purity. Now that the CO2 is concentrated, it can be compressed. Above 1100 psi, the CO2 goes through a phase change from gas to supercritical dense phase. This dense phase allows for much smaller pipelines and dramatically reduces the cost of transport to the final storage or utilization location. For ship transport, the CO2 would be liquefied. So what can we do with that purified CO2 stream? One route, which will be limited in the overall amount of CO2, is the utilization path. The CO2 can be mineralized in concrete blocks, for example, or can be combined with hydrogen to synthesize low-carbon liquid fuels. Some of these paths, such as mineralization in concrete blocks, will result in long-term CO2 storage. Others will not. Life cycle analyses are crucial to have a good understanding of the overall CO2 avoidance. Ultimately, to avoid CO2 emissions at the multi-gigaton scale, the way to go is to geological storage in saline aquifers or depleted hydrocarbon reservoirs. In that case, the CO2 is injected miles below the surface in porous and permeable rocks, where it will be safely and permanently stored. At Total, 10% of our R&D budget is devoted to our flagship CCUS program, directly aligned with the broader Total strategy to be net zero by 2050. We advance a wide range of technologies from CO2 capture to CO2 utilization and storage, as well as the CO2 transport piece. CO2 capture topics cover multiple sources, ranging from atmospheric CO2 to gas power plants, cement and steel plants, and hydrogen production from natural gas. There's no single fit-for-all purpose capture solution, but rather a variety of technologies best suited on a case-by-case basis. The same can be said about CO2 utilization, leading to the manufacturing of low-carbon products such as e-fuels, concrete blocks, or ethylene, to name a few. On the other side, the major focus on the storage side, the major focus is on saline aquifers, which represent the greatest potential to store gigatons of CO2 in order to have an impact on the climate. Even though storage in geologic reservoirs is mature, R&D is still needed to develop numerical models covering very large storages at the basin scale. Herve will be focusing on such research currently underway in Total and with partners. Lastly, CO2 transport still requires R&D efforts to develop optimal designs of large ships and pipelines to reduce costs. The thermodynamics of CO2 mixtures with 95% or more CO2 and impurities such as nitrogen, oxygen, nitrous oxides, just to state a few, is very complex. It must be well mastered to reach operational efficiency. In my two last slides, I'm going to present one example of a CO2 capture topic in our CCUS R&D program. CO2 capture by adsorption, add with a D. The technology consists of selectively adsorbing CO2 in nanoporous materials and then releasing that concentrated CO2 ready for transport and utilization or storage. We have partnered with Svante, an extremely dynamic and successful Canadian startup, which is developing a promising, innovative technology. The Svante-led activities, in which Total is also involved, span from lab pilot plants to a full-scale deployment study to capture 4,800 tons per day from a Lafarge-Holcim cement plant in Colorado. In between is a carbon capture and utilization industrial pilot plant in operation at another Lafarge-Holcim cement plant and a 30-ton per day unit. Aside from the Svante development, Total teamed up with the universities of Alberta and Ottawa in Canada to research high-performing materials. I'll get back to that in the next slide. Overall, this is a perfect example of multi-technology readiness level activities worked in parallel, which can accelerate the time to market and at the same time bring continuous improvement to the technology with the pilot operations and full-scale study feeding back to lower TRL research and vice versa. We recently launched a research project with Dr. Arvind Rajendran at the University of Alberta and Dr. Tom Wu at the University of. The objective is to develop nanoporous materials and more specifically metal organic frameworks or MOFs that will be effective when integrated in an adsorption-based CO2 capture plant. The CO2 sources of interest here are the most dilute ones, so from natural gas combined cycle power plants with 4% CO2 to atmospheric CO2 at 0.04%. The materials will have to be very selective to CO2, resistant to water and oxygen, and require low levels of energy to complete the adsorption and desorption cycle. In a nutshell, the starting point of the project is a database containing several hundred thousands of possible materials. Atomistic simulations will be performed on some candidates to predict performances. Once enough materials have been screened, machine learning models will be built to rapidly link the material structure to its predicted performance. Process modeling coupled with molecular simulations and machine learning will also be used to narrow down the candidates. In the end, we expect to be able to down select a few of the most promising materials that will be synthesized, characterized, and then tested in a lab scale experimental pilot plant. This project heavily relies on high performance computing, which is an essential enabler to both rethink and accelerate our research. Ultimately, the goal of our R&D activities is to bring safe and cost-effective solutions to full-scale deployment of CCUS technologies. I now leave the floor to Herve, who will be focusing on CO2 storage and numerical modeling. Thank you.
Hello, everybody. Samuel, can you go to the next slide, please? Thank you very much. So my talk today, I'm going to have the pleasure of connecting the R&D world, the world of what Andrew was describing before, the exascale computing project, and our operations. And here's a simple case where HPC is going to be extremely important: modeling and simulation challenges for subsurface modeling of CCUS operations. So what you see on this slide here is what a typical carbon storage facility may look like. And I've highlighted on this picture 5 possible challenges, and I'll go through each of them one by one. So first, number 1 here is near the wells. When you inject CO2, you may have well integrity, well injectivity problems. You're going to inject a supercritical gas, and it's going to have an impact on the rocks really near your wellbore. This is where the oil and gas and the industry experience can come in and help us. And where you realize then that further out in the reservoir here in this number 2, you will have pressure and stress changes. These pressure and stress changes may lead to fault activations. Further out in number 3, what you want to do is make sure that your CO2, as it moves in the subsurface, stays trapped and goes in places that you want him to stay. Number 4, the seal integrity is covering a whole basin scale approach where you need to make sure that you don't have any leaks anywhere in your CO2 storage. And last, number 5, you have challenges at the surface. When you inject CO2, what you want to control, avoid a surface deformation and seismicity. So why does HPC matter for all of this? Well, if you go to the next slide, Samuel, you will see that we're not the only ones thinking about this as a global problem. Here, I'm showing you 2 reports, one released in September 2017, one released in June of 2019 by a research group called the Mission Innovation CCUS. And it's a group of about 250 experts, including academia, including the industry, including the national labs. And what did they say? Well, in 2017, the conclusions were, or one of the conclusions was that a refocused HPC effort for CCS should expand beyond traditional reservoir simulation. So here we see that we have limits with our traditional reservoir simulation tools that HPC technologies are going to help us overcome. In 2019, they took this a step further. They even said, well, we don't need just to have technology and performance, but we need to have transparency. So establish one or more internationally recognized CO2 storage open source software. So here is where we're starting. We have this complex technical problem. We have the community that is supporting the use of new technology to help us solve it. And we're looking for a transparent and open way of accessing a solution. So if you go to the next slide, this is what our proposition here is. And I want to take the slide by starting that what Andrew said before about partnerships with industry, academia, and national labs is here put to good use. I will say this is one example of such a successful partnership between Stanford University, Lawrence Livermore National Labs, and Total. And as a matter of fact, as Samuel said, the reason why I'm in California is to be at the heart of this ecosystem between Stanford and the national labs. So what is it that we're doing? Well, we're doing this code called GeosX, and if you're familiar with the ECP project, you may be familiar with GeosX. It's a reservoir simulator that goes beyond the limits of actual existing reservoir simulation tools by going to a multiphysics problem solved in a multi-scale way for HPC. So let me explain those three important words. So multiphysics, why? Well, as you've seen on my first slide, it's not just about capturing mass transfers. It's also about capturing the deformations, the geomechanical deformations that are to this mass energy trend. Why do we want to do that at a multi-scale, with multi-scale approaches? Well, it's a problem that is extremely localized near the wells, and it's also a problem that is very global. You need to cover and simulate an entire basin, which is a set of connected reservoirs, and you want to have the capabilities of starting with a relatively broad and coarse resolution and go to a relatively fine and precise resolution as you wish. And multi-scale in time as well, because you're going to need a lot of resolution to the near well first time steps, and you're going to have a lot of you're going to need a lot of time to simulate centuries of CO2 storage injection. So HPC is really key in this technology, in this application cases, because not only do you need to change your software model, but also you should think about the hardware architecture that you're going to target, and you are going to think, as Andrew was saying earlier, about portability to multiple types of architectures, multi-GPU, heterogeneous GPU systems. And open source LGPL 2.1 is very important for us. We want transparency in this, so GeosX is a program that is going to be, or that is already accessible to the community. Next slide. So here, the key message for my part is that HPC makes multiphysics simulation possible. Without this kind of technology, we couldn't do problems like CCUS. Why? Well, on the left-hand side here, the key message is that we need to be ready for exascale computing. So we need to design and test directly on our HPCs. For that, we have a continuous integration and continuous delivery chain in place. We measure scalability using national lab libraries. Caliper is one of them. We use portability layers that Andrew was mentioning earlier, Raja and Chai for memory management. And everything is accessible in GitHub and is LGPL 2.1. We designed the code for scalability. We start with coupled physics in mind. So this is very important. And this echoes what Andrew was saying earlier about the entire stack needing to be revised, not just the data structures, but also the algorithmic and the discretization models. We use multi-scale algorithms, algebraic and geometric multi-scale algorithms to ensure performance and to ensure that we can reach far out into our reservoir and far out in time, and we adapt to multiple solvers. So here, our linear algebra interface is relatively generic, and we can use tools that the labs have been developing, such as Trilinos or Hyper or PETSI, without necessarily picking a winner at this point. Next slide, please. Here, I'm going to show you one of the dimensions of the problem. It's really the research and development dimension, and these are some results that we have been able to get with GeoSAX. So here, what you see is a CO2 injection simulation for about 100 years. The reservoir, the subsurface reservoir that you see here is faulted. It's built on an unstructured grid, and that grid has been populated using geostatistics with heterogeneous properties. The discretization methods that we used are called mimetic methods. They are very useful because they allow for great parallel performance and are scalable even when you chop your domain in very fine pieces. This is a real data set. It's a Gulf of Mexico data set. And the data is courtesy of the Gulf Coast Carbon Center. And we have run this in parallel with linear solvers, with great linear solver scalability, and we have been able to do pressure evaluations, CO2 saturation evaluations, so we know where the plumes of CO2 are going, but also geomechanical deformations, so we understand the elastic and plastic changes in the rock, which would not be possible without a multiphysics approach. This is very research and development at the moment, but as you will see next with Jorunn's presentation, there's a direct connection between those R&D efforts and production environments, operation environments, such as the Northern Lights project. So I am now going to leave the floor to Jorunn to present.
Thank you, Herve. Now back to the real world. Northern Lights is CO2 transport and storage, and it's part of a Norwegian full-chain carbon capture and storage project, which is named Longship. On the left side here, you can see the full chain from source to sink. You have Norcem. It's an industrial emitter, a cement plant in the Heidelberg group, and also Fortum, that's the waste incinerator, and both of them are located in the eastern part of Norway. So after the CO2 is captured from these two plants, the CO2 will then be transported to a ship in the western part of Norway, Naturgassparken, where it will be offloaded and sent by pipeline to a permanent and safe storage underground. Some more details on the sketch to the right. Northern Lights is the shipping and storage part of the full chain project. It includes ship transport of liquid CO2 from the harbor close to the industrial capture sites, an onshore facility for receiving an intermediate storage of the liquid CO2 from the ships. Further, the CO2 will be transported by offshore pipeline around 100 kilometers long that runs to the subsea template where the CO2 will be injected and permanently stored in a saline aquifer. And that's located around 2,800 meters, almost 10,000 feet below the seabed at the Norwegian continental shelf. So this infrastructure has been designed to allow for capacity expansion in phases, where the first phase allows up to 1.5 million tons CO2 transported and stored each year, and phase 2 up to 5 million ton CO2 a year. But the offshore pipeline is designed to transport 5 billion ton a year from the start. So the shipping solution is chosen here, and that's because it's flexible and scalable. And it's accommodating volumes from multiple emitters, not only from the two here in Norway, but also from European emitters in the future, as you can see the green arrows here on the map. So this project is designed to enable like a carbon removal ecosystem, bringing together European actors across the CCS value chain. And the partners in this project is Total, Shell and Equinor. And we are equally sharing the ownership. And the aim for this project is to be like a kickstart of a decarbonization of the industry in Europe. Next slide. Thank you. So just to give you a flavor of a timescale and some of the major milestones in such a pioneering project, the concept study between the partners started in the autumn 2017. And the next milestone you can see here was the award of the exploitation license. So after the government established a necessary framework, EL001 was awarded to the Northern Lights project January 2019. And when we drilled a verification well early last year, we were pleased not to find any oil or gas. And with the information from this well, the partners took an investment decision in May, and the state took the investment decision in December last year. And now we have just started construction of the onshore terminal in Naturgassparken. You can see some fresh pictures on the lower side of the slide, blasting rocky hill to construct this onshore receiving terminal. And the last picture is a visualization of a finalized site. Last week, the Northern Lights joint venture company was established, and today, actually, the managing director of this company and the Minister of Petroleum and Energy in Norway signed the state support agreement. So this is forming as we speak. And we plan to start the CO2 injection in 2024. Next slide. So what was the enablers and how can this newborn company develop? One fundament here is the partners behind. Majors in the oil and gas industry are in collaboration with the Norwegian state. The Norwegian state is funding partly both CAPEX and OPEX for the first phase. It's also the first commercial CCS hub offering shipping and storage services of CO2 to European emitters, and we have seen a huge interest from the European industry for using the Northern Lights shipping and storage services. And also from extensive oil and gas activities for more than 50 years in Norway, the ecosystem is in place. We are used to drilling wells and huge industry projects. So that is also an important element here to reduce the risk and to make such a project possible. Also, one line on the European context. Europe has a carbon credit system. So where there's certain industries have to buy quotas to be allowed to emit CO2. So we call it European Trading Scheme. From this graph, you can see finally an upwards trend for cost of buying quotas. So this helps the emitters to justify investments in carbon capture facilities and eventually then to buy CO2 transport and storage services for Northern Lights. That is one important element to create this positive business case. In addition, several countries now are planning for national schemes. And one example that is mentioned here is the Norwegian government. It just now in January this year launched a new climate plan. And they plan to more than triple the national tax on CO2 emissions by 2030 to help reaching their country's climate goals. So the market is really developing now. Next slide. So more to the context of this conference. We have agreed with the state on this subsurface monitoring scheme. As long as Northern Lights inject CO2 and operate the storage location, Northern Lights will be in charge and carry risks and liabilities of the storage site. When the injection is stopped and the well is plugged, or several wells, Northern Lights will still need to monitor and carry the risk for minimum 20 more years. Then the license will be handed over to the state and the liability as well. But Northern Lights will still pay for the monitoring cost for another 30 years. So that is the monitoring plan agreed. We have also included a link here for a Norwegian CO2 storage regulation. If you want to read that, you can read about criteria for evaluation of possible CO2 storage site and also how to establish a monitoring plan and a post-operation plan for CO2 storage. So that was a short insight to some of the Total CCUS activities. Thank you for listening in. And we open for questions.
Okay, so yeah, thank you for a great flyover on how technology goes from concept to business. But I think I must say, Jorunn, that it's the first time I've ever heard of an oil and gas company being happy to not find oil and drilling a well. So I would also like to extend a big thank you to IBM for sponsoring this session, as well as remind you to write your questions into the chat, which we did receive some questions. So if we're not able to get to all of them, I will try to follow up directly with any of you if we're unable to answer your questions. So the first question I think is business related, and it is, if CCUS is an essential enabler to reach net zero, then why are the activities not taking off at a more rapid pace across the energy industry? Maybe I think, Sebastian, are you able to maybe chime in on this question, or Samuel?
Yeah. Good morning, everyone. Yeah, I'll try to give try to answer that one. So first of all, it was not presented so far, but developing a full CCUS chain, so capture facilities, shipping, and storage facilities involves a huge investment. I mean, basically, we're talking about it's multi-billion dollars investment, so it's a lot of money. It's also, to some extent, still a new, using new technologies, especially for shipping. So you need a little bit of time to mature this new type of business, so that the customers they get confidence in this new type of technology, and their comfort to enter into commercial contracts. So a lot of money, new industry. And obviously, when you're potentially when you're a big industrial emitters, you're gonna have a look at your alternatives. So what's your alternative in Europe? It's easy peasy. Huh? Either you emit the CO2, or you decide to purchase a service, which is shipping and storage service, and you need also to invest on your side to capture and liquefy the CO2. So your alternative is to emit CO2 to the atmosphere. What's the cost? And so all is related to national carbon taxes, European carbon taxes. If your tax is high enough to incentivize entering into contracts with, for instance, Northern Lights here, then you will go for it. If your taxes are too low, well, you prefer just to pay and emit CO2 to the atmosphere. Of course, it's not only that, because over the midterm, the long term, there is also there are other considerations, like you may be willing, to sell products that you have manufactured, where you can say, well, it's a green product because there is no CO2 emission to the atmosphere related to it, and so on and so on. But the basic principle is, where is your alternative? And if your alternative is more competitive, you're done. So I think Jorunn presented that. By 2030, we can see a lot of countries that are willing to rise national carbon taxes to around or above $200 per ton. And the overall CCUS chain, so capture, shipping, storage, more or less you're talking about 150 USD per ton.
Okay.
So you can see that, 10 years from now, obviously it incentivizes customers to enter into that kind of contract.
Okay, thank you, Sebastian. So we got a few more questions. We have about 5 minutes left. So another question that came in the queue is probably directed towards Herve. It says, which performance portability frameworks have been tried, and what is briefly the resulting performance and percentage of like the peak of the hardware?
This is a great question. So the performance framework that we're using right now is built on top of Raja and Chai. We have actually extended Chai to our data structures. So we have a library on top of Chai called LV Array. This one is also open source to help us with our most frequent data containers, sparse matrices, vectors that are arranged in a way that we are happy with. So we haven't tested the entire application. We're testing it piece by piece, and we're doing the tests right now. So for small strain linear elasticity, which is one of the important constitutive relations that we are testing on, we have been able to reach a 5.8 teraflop max out of 7 for a machine in the labs called LASEN. And so there's two things that we need to do now. We need to continue to do these types of benchmarks for flow simulation, and we're working on those right now. The other thing we need to do is take those benchmarks outside of LASEN and try them out on different systems. And for that, I think Total is a great company that way, that we have a number of machines in Houston and in France that can be used to do these types of benchmarks. So if you want transitioning this from a purely R&D into a production environment where we have more constraints and different setups, is very important for us if we want to take that into production.
Okay, so thank you, Herve. So that kind of connects with another question that was asked. We have about 3 minutes left. Maybe I can shed a little light on this final question. It says, what percentage of Pangea's workload is used for CCS? So Herve briefly mentioned it. He does use the R&D partitions of our machines, which we have based in Houston, and also using machines in the lab. Keeping in mind that Pangea is a production machine, we do carve out. Actually, there are 2 systems still in operation, Pangea 2, Pangea 3. And we do carve out a portion for pure R&D. Roughly 20% of the machine can be used when there's not production workloads. So the CCUS kind of falls into the R&D partition, and it can be pushed out, unfortunately, when there is a production workload that needs to come in. So we are continually expanding our research resources, also based in Houston, to give more computing cycles to these types of efforts. So with that, we're going to conclude to keep things moving along on time. Also, I want to point out, if you missed an earlier session, you can look back in the past content schedule to look at the recorded sessions. And there's also going to be a brief break at this time now. So we're going to restart again promptly at 10:35 a.m. Central Time. So thank you for joining us, and have a good conference.